So far, we've been computing flux and circulation in two-dimensional space. Now we want to move into three-dimensional space. And when we're in three-dimensional space, we'll be talking about surfaces. So we're going to be looking at surface integrals or integrating over a surface. Just to review, previously we were looking at curves with respect to arc length, and then we integrated with respect to a line integral. Our descriptions were one parameter, such as t. Now we're going to be in surfaces. We're going to be looking at surface area. We're going to integrate across the surface, so these are called surface integrals. And our descriptions will be two parameter descriptions. So first of all, when we talk about a parameterized surface, what we're going to do is, well, let's review in two-dimensional space. We had a single variable t, so our vector was x with respect to t, y with respect to t. And our t varied from some a to b value. So now that we're in three-dimensional space, we're going to be looking at a vector representation with a u and a v. So x is a function of u and v, y is a function of u and v, z is a function of u and v. And now this is a vector equation. So our parameters u and v are going to vary over a rectangle where u goes between some a, b value, v goes between some c and d value. Let's look at the diagrams down here and see what we're talking about. So notice that we have in the first diagram, this is our parametric representation. Since there's two variables u and v, we have two axes, u and v, and it's a rectangular region. And that can describe our surface, which is usually described with an x, y, and z. So what we're actually doing here is we're doing a transformation from a uv to an xyz, or from an xyz to a uv. So we call this transformation a mapping. So we're going to take a rectangle in the UV plane and we're going to map it to some surface in the XYZ space. We're going to look at some common surfaces and some common parametric representations. So you're free to use these as a template. Cylinders, and that's going to go back to the way we described cylinders when we did cylindrical coordinates, and we're also going to look at spheres and spherical coordinates again. So Cartesian or XYZ coordinates for a point x, y, and z, recall that x is a cosine theta, y is a sine theta, where theta goes from 0 to 2 pi. Z is just going to be the height of the cylinder, so it's going to go from some 0 to some h value, some height. So the radius is a and the height is h. So here we're assuming that this is going to have an axis of rotation along the z-axis, meaning it's symmetrical about the z-axis, because really we could put our surfaces anywhere we want. So let's make it easy on ourselves and plop it down so the center is with respect to the z-axis. So now our goal is to take all of these variables and write a parametric representation with just u and v. So we're going to let u equal theta. Now this is a parametric description, so this is not unique. This is just usually the easiest way to describe parametrically with u and v. So we're going to let u equal theta and v equal to z. So the parametric description that you can use is r of uv would be the x, the y, and the z. But remember what x is. So this is a cosine u, a sine u, and v is just the z value. So here u is going to go from 0 to 2 pi since u is theta. V is going to vary from 0 to h. And then we have a diagram with what that looks like. We're taking this rectangle where u goes from 0 to 2 pi and v goes from 0 to h. So we get this rectangle and we're mapping it to describe our cylinder. So again, this is just a template for you to use if you have to parametrically describe a cylinder. The next thing we're going to look at is a cone. So when we look at a cone, again, we're going to be using some common variables. This time we're going to use an r, theta, z, so like polar, right? Our r value is going to go from 0 to some a value. So let's look at this blue cylinder down here. You could see that a is the maximum radius in the cylinder. And here, remember, we're just describing a surface. We can put this cylinder anywhere we want in the XYZ plane. So we might as well put the cylinder so that the vertex, it's upside down, and the vertex is at the origin, and then it just goes up from there. So that way the height would just correspond to whatever z value we have. So it's going to make the math easier. Theta is going to go from 0 to 2 pi. Z is going to be described, z is just the height. So z is equal to h, and think about any point on our surface. If you take any point on that surface, it's going to have this r value, but the r value and the a value will be the same. So this is z equal to h. So if we take r over a, that's just 1. So it's still z equal to h. So z is going to be equal to r times h over a. And the only reason why we're writing it that way is to do some really nice math. So if we take that z equation and we solve it for r, we have r is equal to a times z over h. Then, since x is equal to r cosine theta, using those polar forms, and y is equal to r sine theta, we can simply replace the r value with a times z over h, still have the cosine theta, replace the r value with a times z over h sine theta. And now our r of uv can be written as av over h cosine u, since u is theta, and v is z. So the next coordinate is av over h sine of u, and the z value is just v. So now we've written this cone that was originally with an x, y, z in terms of two variables, u and v. So again, you can just use it now that we've talked about it. Let's look at spheres. So we're going to go back to our spherical coordinates. So remember that was a rho, phi, theta. Here, rho is going to be equal to a. When we look at the diagram below, the a value is this distance out. So it's a radius, right? So that would be that distance out. Our phi goes from 0 to pi. So these are just the same parameters we had before when we did spherical coordinates. And then theta goes from 0 to 2 pi. So the x value is going to be a sine phi cosine theta. Y is going to be a sine phi sine theta. And z is a cosine phi. So if we let u be phi and v be theta, then the parametric description r of uv is going to be a sine u cosine v, a sine u sine v, a cosine u. Here u goes from 0 to pi, v goes from 0 to 2 pi. Now, what if you had a surface that wasn't of the previous forms that we talked about? Well, then you have to describe it using u and v instead of, in this case, example 1, we have an x, a y, and a z. In example 1, we're trying to find the parametric description of a plane. And usually when you work with planes, just take one of the variables. I'll just use z because that's what we usually do, but it doesn't really matter which one you choose to solve for. I'll just take this equation and solve it for z. So I have 2 minus 2x plus y. Now something to notice is that in a plane, the values for x, y, and z go from negative to positive infinity. So I'm going to put them all in one inequality from negative to positive infinity. Now remember, this is not unique. Parametric descriptions are not unique. So now I have to define my u and my v. So I have the z by itself on one side of the equal sign. On the other side, I have x and y. I'm going to simply let u equal the x value, v equal the y value. And then my r function, my r vector function would be an x, y, z. So x is simply u, y is simply v. Z is 2 minus 2x plus y. So that's 2 minus 2u plus v. I also have to state that my u and my v vary from negative to positive infinity. Remember, that is not unique. Okay, so this is not unique. You could have easily solved that equation for, say, y, and then let u be x and v be z, and done the same thing. We'll look at another example, one that's a little bit more complicated. Example 2, we want to find the parametric description for a hyperboloid. So a hyperboloid kind of looks like a cup, right? It's rounded, so it kind of reminds me of a cone. And I'm thinking that, okay, I have to get down to 2 variables. I have 3 variables. I have an x squared plus y squared. That reminds me of a polar form, right? So I'm going to try polar form, and I'm going to kind of use what we had with the cylinder and the cones, kind of use that example, maybe try the more like a cylinder example. See how it turns out. I know that x squared plus y squared is r squared. And in polar, x is equal to r cosine of theta. Y is equal to r sine theta. So I have my x and my y. I am simply going to let my z value equal z for now. See what happens when I play around with this a little bit more. So since z squared is equal to 4 plus r squared, then z is equal to, and I don't need the negative. Usually when you square root both sides, you have a plus minus, but notice my z values are going from 4 to 9. They're always going to be positive. So z is going to be the square root of 4 plus r squared. And now I have to define my u and my v. So I know that x is r cosine theta, y is r sine theta. So I have an r and a theta. So it makes sense for me to try u equal to r and v equal to theta. And then I'll see what happens. So my r of uv would be, my x is r cosine theta. So that's going to be u cosine of v. My y is r sine theta, so that's u sine of v. My z value is just z. However, I know that my z value is the square root of 4 plus r squared. So my z value is the square root of 4 plus r is u, so that's u squared. And now I've written this hyperboloid in terms of a 2-variable vector function. All right, so what are the parameters on my u and my v? Well, my v is equal to theta, and the hyperboloid goes all the way around. So I know my v is going to go from 0 to 2 pi. So I just have to figure out what u is. So remember, u is equal to r, and I know that, I'll do this off to the side, I know that my z value goes from 4 to 9, and I know that z is equal to the square root of 4 plus r squared, or 4 plus u squared. So now all I have to do is algebraically solve for u by squaring everything to get 16 less than or equal to 4 plus u squared less than or equal to 81 minusing 4. So that's 77. And then I'm going to square root everything. So remember that I'm not looking at the negative, I'm only looking at the positive. So it's going to be the square root of 12 less than or equal to u less than or equal to the square root of 77. Coming back here, I know that my u would be square root of 12. What is that? 2 square root of 3. Square root of 77, I can't simplify that. So I have my parametric description of this hyperboloid. Now that we know how to describe surfaces, we're going to define our surface integral. So when we define our surface integral, we're going to first look at our parametric representation of r with respect to the two variables u and v over the region uv. Now remember, r is describing a surface in vector form. So at any point on the surface, we're going to have tangent vectors. When we find our tangent vector, we take the derivative of r. Since r is written in terms of two variables, we're going to have two tangent vectors, and we're going to compute the partial derivatives. So to find the tangent vector with respect to the variable u, it's the partial derivative of r with respect to u. To find the tangent vector with respect to v, it's the partial derivative of r with respect to v. Necessarily, whenever you take two vectors and you cross them, you get a vector normal. So to find a normal vector to our surface, we just take the cross product of those two tangent vectors. So our surface integral is going to be a double integral over a surface. This ds, the s is not arc length, it's surface. That double integral is hard to work with, so we're going to work with our parameterized form over our region R. And since we're doing a transformation from a surface to an area of that region R, so we're going from a ds to a dA, we're going to have a Jacobian. The Jacobian turns out to be the magnitude of our normal vector. So it's going to be our function times the Jacobian, which is the magnitude of our normal vector. In the event that the integrand is 1, then our integral is just equal to a surface area. So previously, when an integral was 1, then we were finding an area. But now since we're on a surface, we're finding a surface area. So I'll just use SA for surface area. In example 3, we want to find the surface area of a sphere of radius 2 centered at the origin. So since I'm supposed to find surface area, my integrand is 1, but remember I still have to compute this Jacobian, which is the magnitude of that normal vector t sub u cross t sub v. This is a sphere, so I can use my definition of sphere that we had talked about earlier, where my radius is 2, centered at the origin. I'm just going to follow that definition of a sphere. I'm going to let u equal to phi, v equal to theta. And then I describe r of uv as 2, because my radius is 2, sine of u cosine of v. And then 2 sine of u sine of v. And the last component would be 2 cosine of u. Now just remember your u value is phi, so it goes from 0 to pi. V is theta. It goes from 0 to 2 pi. Now to compute my surface area, To compute my surface area, I'm going to do a double integral over my region. My region is my u and my v values, so maybe I'll do 0 to 2 pi. I'll do the v on the outside and my u on the inside from 0 to pi. My integrand is 1, but I still need to compute the magnitude of my normal vector, which is just the cross product of these two tangent vectors. So that I have to still figure out. And I have the order as du dv. But these are constant limits of integration, so you could have changed it and done it in a different order. Okay, let's do the cross product, and this is going to be hideous. But once we compute it, you won't have to compute it anymore. Okay, so I'm going to have an I, a J, and a K. Let's see if I have enough space here. So to compute T sub u, it's going to be the partial derivative of r with respect to u, which is partial derivative of x with respect to u, y with respect to u, z with respect to u. Going back to my definition of r, that first component is the x, and then I have a y, and I have a z. So the partial derivative of x with respect to u is going to be simply 2 cosine of u cosine of v. So 2 cosine u cosine of v. The next component would be 2 cosine u sine v. And then the last would be a negative 2 sine of u. And now I have to do the partial derivative of x with respect to v, y with respect to v, and z with respect to v. This becomes a negative 2 sine u sine v. The next component would be 2 sine of u. That's doing this weird thing. Sorry. 2 sine u cosine v. And then 0. That would be equal to the I component is 4 sine squared u cosine of v minus, this becomes a negative 4 sine squared u sine v. That's my j. I'll put my k, stop that. Ugh. I will put my k down below. That's going to be 4 sine u cosine of u cosine squared v plus 4 sine of u cosine of u sine squared v. And that's my k. think I'm going to clean this up because notice in my k, if I factor out 4 sine u cosine u, what remains is cosine squared v plus sine squared v, which is simply 1, and they'll cancel. So I'm going to factor out a 4 as well and write this as the vector, I don't like ij, of sine squared u cosine v. The next component would be sine squared u sine v. And then the last component would be sine u cosine u. When I find the magnitude of that vector, I can factor out the 4. And then compute all of this. Sine squared u cosine of v squared plus sine squared u, sine of v squared plus, my pen is dying, sine of u cosine of u squared. And I'm going to do this on the other page. Okay. I have the 4 out. Let's see, I have sine to the 4th u cosine squared v plus sine to the 4th u sine v, sine squared v, sorry. And then plus sine squared u cosine squared u. Huh. Okay. Let's see, if I combine these first two, I could factor out the sine to the 4th. Will that help me? What's left over would be the cosine squared sine squared v. Those will cancel. So I will have sine to the 4th u plus sine to the 4th u. No, I'm factoring out sine to the 4th. I'm doing algebra in my head. That's scary. And then I'd have a 1 plus sine squared u cosine squared u. And then factoring out the sine squared, that will give me a sine squared u plus cosine squared u. I didn't have to write that. I could have seen that that canceled. Okay, so this is gone. It's just 1. And then the square root of sine squared u would just be sine of u. This ends up to be 4 sine of u. And that was the cross product of those two tangent vectors. Now remember, my u value went from 0 to pi, and I'm looking at sine of u. So that would be sine, it'd be like quadrants 1 and 2, right, if you're looking at the unit circle. So the sine values are never going to be negative when I figure out this magnitude, because that's what I was supposed to be figuring out, right, the magnitude. So when I figure out the magnitude of 4, don't know what's going on with my program, of 4 sine of u, I don't need those absolute values. It's just 4 sine u, since sine is never going to be negative. Putting all of this together, I get the surface area, going back to my integral, 0 to 2 pi, 0 to, stop this, 0 to pi of 4 sine u du dz, or dv, is going to be negative cosine u, negative 4 cosine of u, 0 to pi dv. Okay, so that's going to be 4 plus minus a negative 4, so 8. And that's 8v. It looks like it's going to be 16 pi. That's the surface area. I did want to bring your attention to this magnitude of these tangent vectors, their cross product. Remember that was 4 sine of u? Okay, so something to keep in mind, that r was equal to 2 and 4 is 2 squared. So this is the same as r squared sine of u. So in general, for any sphere centered at the origin with r equal to some a value, we could write the magnitude of these two tangent vectors, oops, as a is my radius, a squared sine u. So you can just use that since we already showed it. So for any sphere of radius a. And then notice also that 16 pi is equal to 4 times r squared pi. So the surface area for any sphere centered at the origin is going to be 4 a squared pi. And here a is equal to the radius. So now you never have to do that again. You can just use the cheats that I've given you. In example 4, it says find the surface area, which is good because at least I know that the integrand, oh, let's do it again. I know my integrand is 1. I have a cylinder of radius 2. My z values are going to go from 0 to 8 minus x. So these are actually planes. Let me see if I could do a quick sketch, a sad sketch. So z is equal to 0. They'll have a cylinder down here, but there's going to be this plane that's chopping off the top part of it. So the plane above is going to be slanted. So something like that. Apologies again for my drawing. So since it's a cylinder, I'm going to follow the template where my u is going to be equal to theta. And my v is going to be equal to z. So r of uv is going to be 2 cosine of u, 2 sine of u, and then v. Okay, so now all I have to do is figure out the limits of integration for my u. Since it's theta, it's going to go from 0 to 2 pi. I think I'm going to have to do something about this program. And then my v values are going to go from, or I just followed the z values that were given. So z is going to go from 0 to 8 minus x. So v is going to go from 0 to 8 minus my x value is 2 cosine of u, right? Because this is my x, my y, and my z. The next thing to do is to compute the cross product of these tangent vectors with respect to u and v. I, j, k. Looks like it's going to be negative 2 sine of u, 2 cosine of u. K would be 0. And then it looks like it's going to be 0, 0, 1. Well, that's not too bad. The last example was horrible. Let's see, we have 2 cosine ui. Then the next one should be minus and negative, so plus 2 sine uj. And then 0k. So figuring out this magnitude, it's going to be equal to, I can pull the 2 out and then just do the square root of, I think my program's getting too sensitive. Pull out the 2. This is simply cosine squared u plus sine squared u, and that's just 1. So it's 2. And then computing our surface area, I have my integral. I'll go from 0 to 2 pi. I want to end with constants because this time I have a variable limit of integration, 0 to 8 minus cosine of u. And this is 2. I'm going to do dv first and then du. Yeah. I could pull out the 2, but I'll just leave it there. I'm having issues with this program. Okay. So this is going to be 2v. I'm going to evaluate it from 0 to 8 minus cosine of u. We're going to go from 0 to 2 pi of 16 minus 4 cosine u. Du. And then that would be 16 u minus 4 sine u, 0 to 2 pi, 16, 32 pi, let's see, sine of 2 pi, sine of that's all 0. So it looks like it's just 32 pi. All right. In example 5, we're going to look at an application of these surface integrals. Example 5 says the temperature in degrees on the surface of a particular sphere of radius 2 centered at the origin varies according to this function, 1 plus sine phi. Phi goes from 0 to pi. Theta is going to go from 0 to 2 pi. We want to find the average temperature over the sphere. So whenever we're integrating and we're trying to find an average, remember we also have to divide by whatever the area of that region is. So we're trying to find the average over a surface. So we're going to do the surface integral, and we're going to divide by the surface area. So surface integral divided by surface area. So that would give us the average over the surface. So it's the average temperature over the surface, which is a sphere. Since I am looking at a sphere, I know how I'm going to represent that parametrically. I also have a lot of nice things that we already figured out in a previous exercise. I know what my surface area is. We already figured that out. We have a radius of 2. The surface area is simply 4 times r squared pi, or 16 pi. I also know that the magnitude of the cross product of these two tangent vectors is going to be a squared sine u, or 4 sine u. Again, we already figured this out previously. So now all I have to do is represent my region parametrically. So our usual, we're going to let u equal phi and v equal theta. So I know that my u value is going to go from 0 to pi, and my v will go from 0 to 2 pi. My average temperature is going to be equal to, I have to divide by the surface area, so that's multiplying by 1 over 16 pi. My region, and here it doesn't matter if you do UV or VU, I'll just do the usual 0 to 2 pi on the outside. So that's V, and then U would be 0 to pi. My function is 1 plus sine of phi, but phi was U, so 1 plus sine of U times my Jacobian, which is going to be 4 sine of u du dv. And I'm going to get rid of the parentheses. So now it's just computation, straight computation. And write this as 4 sine u plus sine squared u du dv. So the sine squared u, actually it's 4, sorry. 4 sine squared u. So this 4 sine squared u, going back to trig, I can write that sine squared u is equal to 1/2 1 minus cosine of 2u. So if I multiply that by 4, that's just going to be 2 minus 2 cosine of 2u. So we have 1 over 16 pi, integral from 0 to 2 pi, integral from 0 to pi. And this is going to be 4 sine of u plus 2, minus, sorry, minus 2 cosine of 2u du dv. Integrating with respect to u, I have negative 4 cosine u plus 2u minus sine of 2u. And we're going from 0 to pi. Let's see, so pi, it's going to be a positive 4 plus 2 pi. And then that's a 0 minus a negative 4. And a bunch of zeros. All right, so it's going to be 8 plus 2 pi. So since it's 8 plus 2 pi, I can bring that out since it's a constant and just integrate with respect to v. Looks like, should I simplify it? 8 plus 2 pi over 16 pi. Yeah, I could reduce it. So this is v 0 to 2 pi. So just multiplying that by 2 pi. But then the pi's cancel, and this should be over 8. That should reduce to 4 plus pi over 4. Now remember, this is supposed to be the average temperature, and it was in degrees, so I have to add the degree symbol for my final answer. Now this should be the exact answer of the average temperature over the sphere. So when you think about this and how you could apply something like that, think about the Earth. At the poles it's colder, at the equator it's warmer. So if you're trying to figure out the average temperature over the surface of the Earth, you could use the same process. Let's see, if I was to plug this, answer kind of doesn't make sense. If I were to plug this in a calculator, I get 1.8 degrees. That I can imagine. But with all the 4s and pi's and all that stuff, it's harder for me to visualize. Okay, so we're going to move on and we're going to look at surface integrals again. So we're still doing surface integrals of scalar valued functions. So of explicitly defined surfaces. So when we explicitly define a surface, that means we're going to take the z equal to some function of x's and y's. So this is going to be z equal to a bunch of x's and y's. So if you have your surface already defined in that way, then you can use this alternate version of the surface integral formula. So again, we're going to be integrating over some surface, so it's a ds, but then we'll look at this region. And this region R here is in the xy plane. So we're not going to be looking at a function uv that's vector valued. We're going to be just looking at x's and y's and our z equal to some function of x and y. So what happens to the magnitude of that normal vector? We still have our function. It's an x, a y, and a g of xy. That's our z value, right? Well, thinking about it this way, if the tangent vector with respect to u, that would be, might be a little bit hard for you to imagine this. That if we're looking at the xy plane, that could be seen as that unit vector 1, 0 along the x-axis. But then when we figure out the vector with respect to z, that's where we take the partial derivative of z with respect to x. And then when you look at the tangent vector with respect to u, since we're not writing our equation in terms of a vector valued function uv, I am translating this back to x, y, and z. It would be a 0, 1. It's a 0, 1 because we're going along the y-axis this time. And then we're taking the partial derivative of z with respect to y because we're trying to find the rate of change of our z function. It's written explicitly as z. So partial derivative of the z with respect to x, that's a z value, partial derivative of z with respect to y, right? So that's what they would correspond to. And when you take the cross product of those two vectors and then take the magnitude, that's what you get in this formula here. You get the square root of the partial derivative of z with respect to x squared plus partial derivative of z with respect to y squared. And there's going to be a plus 1. So you can go ahead and verify that by cross product of those two vectors, and that's what you should get. Let's go ahead and apply this. In example 6, it says to find the surface area, which is awesome because we have that same property that we have an integrand of 1. Doesn't matter if it's written parametrically in terms of some r of uv or written in terms of z equal to something with x's and y's. Still, if you find a surface area, integrand is 1. So we're finding the surface area of this cone, z squared equal to 2x squared plus 2y squared, where our z values are going to go from 0 to 2. It says to use the explicit description, which means what's in the box up here. So first of all, our surface area that we're looking at is going to be a double integral over our region. Since our function is 1, all I'm computing is the square root of the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared plus 1 dA. So that's what I need to figure out. So how do I do the partial derivatives? Well, you can solve it for z, but you'll get a plus minus with the square root. So instead, I think what I'm going to use is I'm going to use implicit differentiation. So remember with implicit differentiation, we take all the derivatives as it's written. So if I take the derivative of z squared and z is my function, it becomes 2z times the partial derivative of, if I'm taking the derivative with respect to x. And then on the other side, taking the derivative with respect to x, it's going to be 4x. Or in other words, the partial derivative with respect to x is equal to 4x over 2z. And then I can reduce that to 2x over z. So the partial derivative with respect to y is going to be same thing. We'll end up having 4y over 2z. Which would be equal to 2y over z. So I'm going to plug that in. I'm not going to worry about my limits of integration just yet. It could happen that all of this turns out to be a constant, and if it does, I don't even have to figure out limits of integration. And I'll show you in just a second, because this actually does turn out to be constant. All right, this would be 2x over z squared plus 2y over z squared plus 1 dA, kind of scrunching this all in. And then that's going to be 4x squared over z squared plus 4y squared over z squared. Why don't I write that all together? 4x squared plus 4y squared over z squared plus 1 all underneath this square root. And then notice that 4x squared, oops, z squared is just 2x squared plus 2y squared. Ah, hate you, hate you, hate you. So 2x squared plus 2y squared, because that's how z was defined, right? Z squared is equal to 2x squared plus 2y squared. And the reason why I did that is because I can see with that fraction, it's just equal to 2. So this becomes the integral of the square root of 2 plus 1, or 3. And now I have a constant in my integrand. Notice if I pull it out and bring the square root of 3 out, I'm taking a double integral over some region, dA. Going back to our double integrals, this is simply the usual double integral, which is the area of R. So I need to determine what R is. Off to the side, I'm going to just do a little sketch. R is in the XY plane. My surface is a cone. It's going up. Right, so this is my Z. And then we have X and Y. So remember what we do, we're looking at the shadow. And the shadow in the XY plane is going to be this circle. So this is my region R. It's a circle. And the circle is going to be 2x squared plus 2y squared equal to 4. Or in other words, x squared plus y squared equal to the square root of 2. Or equal to 2, sorry, I don't know why I said square root of 2. Which means my radius is square root of 2, which is why I wrote that, sorry. So my area of R, my region R, is simply the area of a circle of radius 2, and my integral is the square root of 3 times pi r squared, which would be 2 square root of 3 pi. Now I just took the easy way out. Going back to this integral here, I took the easy way out and went, oh, okay, all I have to do is figure out the area of my region, but you didn't have to. You could have set up your double integral. You did have to know that the region was a circle, but if it didn't strike you as, oh, I could just do that geometrically, you could have gone, oh, okay, it's a circle, and describe the area. You're going to have your R values that are going to go from 0 to the square root of 2. You're going to have theta going from 0 to 2 pi. And then you would just do it as normal. Integral from 0 to 2 pi, 0 to square root of 2, R dr d theta. So you could switch it to polar. Why don't I write that out? Or at this point, instead of doing this geometrically, you could have figured out that it was polar. So you would have your R values going from 0 to square root of 2 and theta from 0 to 2 pi. And then your surface area, we already pulled out that square root of 3. You could go 0 to 2 pi, 0 to the square root of 2r dr d theta, since it's in polar form. So if you did compute that, you would have gotten to square root of 3 times pi. All right, example 7. I've been finding surface area, surface area, surface area. So let's do example 7. We want to evaluate the surface integral. So this is not finding a surface area. We have to do the surface integral using an explicit representation of the surface. Now here's our function, z, which is equal to xy. S, our surface is going to be this plane, z equal to 1 minus x minus y. It's in the first octant, so that means that x, y, and z are all going to be greater than or equal to 0. Since I'm using an explicit description, I know that I'm going to have to figure out the partial derivative of z with respect to x. Now, luckily, it's already written out here. So that's going to be super easy. The partial derivative of z with respect to x is just going to be -1. And the partial derivative of z with respect to y is also -1. Oh, that's going to be pretty. Using that explicit formula for a surface integral, it's the function xy times the square root of -1 squared plus -1 squared plus 1 squared dA. And that ends up just being the square root of 3. So I'm going to pull out that square root of 3. And then integrate over this region xy dA. So unfortunately, my integrand is not a constant. I can't just look at this geometrically. But this is just going to be our usual double integral that we had previously. I have to find my limits of integration. So what I'm going to do is, remember what we do. It's the plane z equal to 1 minus x minus y. What I'm going to do is I'm going to let z equal to 0 and then just look at the graph in the xy plane to determine my limits of integration with respect to x and y. So if z is equal to 0, I could write this as, solve it for y and write y equal to 1 minus x. Or I could solve it for x and write it as 1 minus y. It doesn't really matter. The reason why I have to do that is because I need to figure out these limits of integration. So that's what it looks like. Here's my region. So these are my limits of integration. Again, we're just going back to what we did when we first started discussing double integrals. Okay, so if I let my x values vary from 0 to 1, then my y values I have to be careful with, okay? Because think about this, my y value, my smallest y value will be 0. And then as I integrate, this y value here on this slanted line is 1 minus x. And now you didn't have to, you could have let the y values go from 0 to 1, and then your x values could have gone from 0 to 1 minus y. It just depends on how you want to define those limits of integration. So going back to my double integral from what we had at the very start of this semester, I pulled out that square root of 3. And I have to put my x values on the outside because my y values have variable limits of integration. So 0 to 1 for x, 0 to 1 minus x for my y value. This is xy dy dx. And now it's just computation. This is going to be integrating with respect to y, so it's y squared over 2. And I think I'm going to pull out the 1/2 just because I have that y squared. So I'll have square root of 3 over 2. And this is going to be x times 1 minus x squared. At this point, I would simply multiply out the 1 minus x squared and distribute the x. So again, double check me because I'm doing this in my head. I think it is x minus 2x squared plus x to the third. Which would be x squared over 2 minus 2x to the third over 3 plus x to the fourth over 4. And although those fractions are hideous, my limits of integrations are really nice. It's just 0 to 1. So square root of 3 over 2 times 1/2 minus 2/3 plus 1/4. I think that's 1 over 12. I think. The square root of 3 over 24. Again, double check me. I always tend to make errors on those minor computations. Now here what I have is a little cheat sheet. We haven't talked about all these properties, but you're free to use them. In the beginning of this section, we talked about a parametric description. So if you look at cylinder, we had our parametric description that we already talked about with respect to our u and v. What I didn't talk about is our normal vector. So here's a cheat sheet on how you can find your normal vector. And with that parametric description goes an explicit description. In this case, we have x in cylindrical form. We'd have an x squared plus y squared is equal to a squared. Z is going to go from 0 to h. And we also have what our normal vectors would look like. So if you look at this little table, you have your parametric description and then the corresponding explicit descriptions. Remember what we're doing is we're working our way to computing flux and circulation in three-dimensional space. So in this section, we're going to first talk about flux, and then in later sections, we'll work our way towards circulation. Remember flux, when we're looking at two-dimensional space, was a vector field dotted with a normal vector. That was our first definition with a line integral. Well, we haven't talked about vector fields. So now that's what we're going to do. We're going to look at, with respect to these surface integrals, we're going to look at our vector fields. This is just vocabulary right now. So when we talk about a two-sided or orientable surfaces, these are surfaces where the normal vectors vary continuously as you go around your surface, but they stay in the same direction from the start to when you come back around and finish. Okay, so this means that if you travel around the surface, starting and ending at the same point, the normal vector at the start has the same direction as the normal vector at the end. So these are the types of surfaces that we're going to be working with when we talk about our vector field. Let's look at this first donut shape. This is a torus if you're not familiar with a torus. So let's just say I'm starting at this point. I'm going to use the finer pen. Let's say I start at this point here, and I'm on the outside of this torus. So I'm going to have some normal vector pointing outward. And I'm going to travel around my torus and travel around my torus. Then eventually I'm going to come back to the same spot and the normal vector is pointing in the same direction. Now let's look at this next figure. If you're not familiar, this is a Mobius strip. Let's say I start here and I have this normal vector coming outward. Uh, irritating. And then I travel around and travel around and I travel around my surface. But unfortunately, now I'm on the inside. So when I come back around, since I'm on the inside of this figure, the normal vector is going to be pointing in the opposite direction. So in this case, I don't want to consider that type of surface. This is non-orientable. And that's not what we're going to be considering. For our purposes, we're only going to be considering these types, the two-sided or orientable. So at any point on this surface, there's going to be two normal vectors. There's going to be a normal vector that points outward and one inward. So unless you're told otherwise, you can assume that the normal vector that you're going to use is going to point outward. So again, this is just some vocabulary and some review on outward, inward, normal vectors. So let's look at our flux integral, and that's where we're headed here to compute flux in three-dimensional space. So let's say we have a vector field and we're in three-dimensional space, so it's FGH. And sometimes it's helpful to think of it as like the flow of a fluid or transporting any substance. So we're going to have this nice, smooth, oriented surface that we talked about before, the orientable surfaces. And we're going to compute our net flux of our vector field across the surface. So before in two-dimensional space, we're looking at flux on a curve, and it was a closed curve, but now we're looking at this nice smooth oriented surface and we're going to compute flux across the surface. So all we're doing, remember, net flux is we're just adding up all the outward normal vectors. So let's look at what we have here, and this is review. So let's say that we have some point on the surface, and then at that point we have a normal vector. So this first diagram is showing what we mean. So let's say we have this point, we have some normal vector, that's our blue vector coming out to the surface, and then we have a vector from our vector field at that point. Theta is just going to be the angle between a vector from your vector field F and the normal vector at that point. Going back to the definition of cross products, we have that whenever or dot product, sorry, whenever you dot your vector F with a normal vector, it's just multiply their magnitude times cosine of theta, where theta is the angle between them. So that corresponds to the diagram. Now we're going to be looking at unit normal vectors. So if it's a unit normal vector, then the magnitude of n is simply 1, and this becomes the magnitude of f times cosine of theta. So now our special cases, so this should all look familiar to you. In the event that a vector from our vector field and our normal vector are going in the same direction, that means theta is going to be equal to 0. So when we do our dot product, it will simply be the magnitude of f. In the case where our normal vector and our vector in our vector field are in opposite directions, theta is pi, cosine of pi is -1. So the dot product is going to be the negative magnitude of f. And then the other special case would be if the vector from the vector field. And then normal vector at the point are orthogonal, so theta is equal to pi over 2, and orthogonal vectors dot products always 0. And then here's just a note. If you have an explicit form, so z equal to some function xy, then a vector normal to the surface can be written as negative z partial with respect to x, negative z partial with respect to y, 1. So that's a normal vector. Remember, there's more than one normal vector on the surface. Okay, so now let's look at our surface integral with respect to a vector field. This is the flux integral. It doesn't say that, oops, in your textbook, but a surface integral of a vector field is the flux integral. Going back to the line integrals, remember when we did the dot of our vector field with a normal vector, we were computing flux. So this is flux, but instead of over a curve, it's over a surface, which means you have to add in that normal vector, which is the cross of those two tangent vectors. So there we have our flux integral. Again, remember ds is not arc length, it's surface. Same tangent vector with respect to u, which would be the partial of r with respect to u, tangent vector with respect to v, partial of r with respect to v. So all of that is the same. So we know the normal vector would be the cross product. And if it's explicitly defined as z equal to some function x and y, then we can, so here we computed the vector field and dotted it with the normal vector. So if you look at the vector that I had previously written down, this is what we're going to use. Negative f times the partial of z with respect to x minus g partial of z with respect to y plus h. Okay. So that's the form that we want to use because it's usually the easier one to use. If you use f dotted with n, that means you're going to have to compute the normal vector. In example 8, we're supposed to be finding the flux, and our vector field is a three-dimensional vector field. We're given that we're finding the flux across this tetrahedron, z equal to 4 minus x minus y. Okay, so we have a vector field, and we have this tetrahedron. That's our surface. We're plopping that tetrahedron down into our vector field, and we're trying to see how this vector field is going to affect our surface. So one thing we could figure out is we could figure out flux, which is just all the vectors that are normal to our surface. Okay? The other thing we could figure out is circulation, which would be in a later section. We're not going to do it just yet. So the first thing I want to do is figure out what form of my flux integral am I going to use? Am I going to use f dotted with n, or am I going to use that alternate version, the f times the partial derivative of z with respect to x, and so on? Well, no matter what, I could see that since this is an explicit form, I can easily figure out those partial derivatives. Now remember, in my vector field, it's 0, 0, negative 1. That would be my f, my g, and my h. So I have f, g, and h. And it's easy enough for me to figure out these partial derivative of z with respect to x. That's just negative 1. Z with respect to y, that's negative 1. So it seems like the easier form for me to use would be the second form over the region. So it looks like if I was to compute flux, I would want to do the double integral over my region of f, which is 0, times partial derivative with respect to x is negative 1. I'm going to write it out even though I know it's going to be 0. And then it's going to be minus 0 times negative 1. So that's 0. plus negative 1 dA. And this becomes negative 1 for the integrand, which is nice because since it is a constant, I can bring out the negative. And if I look at this integral over the region of 1 dA, this is the area of my region. So what is my region? Well, this region is, remember, this is in the xy plane. So if we go back to our surface in the first octant, and we just go ahead and graph that in three-dimensional space, it may be easier for us to see what our region is in two-dimensional space. But you don't have to do this. So to graph the tetrahedron, remember if I set the x and y equal to 0, I have z equal to 4. Zx equal to 0, y is equal to 4, and then yz equal to 0, x is equal to 4. So here's our tetrahedron, which means if I just want to look at this region in the xy plane, it's going to be a triangle. Okay? And again, it might be helpful if we resketch it so that it's in the xy plane. This is all going back to what we did previously. Which means the area of this region is the area of a triangle, and its area is 1/2 times the base, which is 4, times the height, which is 4. So the area of our region is simply 8. And there's that negative on the outside. My flux is going to be equal to -8. So although it doesn't ask for it, this would be a sink. Now I didn't have to use the geometry, the area of R. I could have gone ahead and computed those limits of integration. Notice that if I'm looking at the region in the xy plane, that I could let my x values go from 0 to 4, and my y values go from 0 to, this is y equal to 4 minus x. Again, I didn't have to use geometry. I could have computed flux equal to the integral from 0 to 4 for my x's, 0 to 4 minus x. And now remember my integrand was -1. This would be a dy dx. If you did compute that, you would still get -8. So again, with these flux integrals, you get to choose. Do I want to figure out what the normal vector is, or do I want to use that other form? And it kind of just depends on what you're given. Example 9 is going to be our last example for this section. I apologize, this is a super long section. So it says to find the flux of this vector field across curved sides of the surface S. S is defined as z equal to cosine of y, where the absolute value of y is less than or equal to pi, and x is between 0 and 4. The normal vectors point upward. Again, I could either use flux equal to the integral over the surface of f dotted with n, so I'd have to figure out what the normal vectors look like. Or I could use the other form. You know what? I might want to try this one just so you can see what it looks like. Going back to our little cheat sheet, I know the normal vectors will look like this: plus or minus, negative partial of z with respect to x, negative partial of z with respect to y, 1. And then I could just choose the one that makes sense with this problem. So the partial derivative of z with respect to x. Again, this is my f, my g, and my h. And I have my z equal to cosine of y, so it's 0. Z with respect to y would be negative sine, but it's a negative, so it turns into a positive sine of y, and then 1. So since I'm choosing upward vectors, I'm going to choose the positive 0 sine. Sine y and 1, right? Because it says I'm looking at normal vectors that are pointing upward. And I have my vector field. Well, let's try to use this formula. I'm not going to figure out limits of integration just yet. I'm going to see what I get when I take the dot of e to the negative y, 2z, xy, and dot it with 0 sine of y, 1 ds. It looks like it's going to be at 0. The sine y would be 2z sine y. Plus xy ds. All right. Now I need to figure out my limits of integration. But luckily, those are already given to me in the problem. Going back here, I'm already given that my absolute value of y is less than or equal to pi, and x values are from 0 to 4. So if I was going to describe this surface in terms of x and y, if I do the x on the outside, it's going to go from 0 to 4. Absolute value of y less than pi means it's going to go from negative pi to positive pi, right? When I remove the absolute values, put it between the negative and the positive. My integrand is 2z sine y, but z is equal to cosine of y. So right now, all I'm trying to do is write everything in terms of x and y. So if z is equal to cosine of y, this becomes 2 cosine y sine y, so that's okay, plus xy. And this would be dy dx. Okay. So if you're going to use that first form, you have to find the normal vector, and then you have to describe the surface that you're given. And we were given the surface as z equal to cosine of y, and we were given our limits of integration. So I'm trying this first form. Since I have most of the information already, I had to do very little computation so far. Let's see, can I write that? I don't want to do a substitution. I have the cosine sine, but going back to our trig identities, this is actually sine of 2y. Otherwise, I would have a difficult time trying to evaluate that integral. Substitution wouldn't work. So the only choice I really have is to use a trig identity. Well, maybe substitution would have. I'd have to split this up into 2 integrals though. I'd have to have one double integral with 2 cosine y sine y plus another double integral with xy. Let's see, now I can integrate directly. This becomes negative cosine of 2y over 2. Plus integrating with respect to y gives me xy squared over 2, which is nice. If I want, I can pull out the half. Negative pi 2 pi. I'll just leave it in. Okay, so it looks like it's going to be -1/2 plus x pi squared over 2 minus, let's see, -1/2 plus x pi squared over 2. I get 0, which means flex is 0. Although it didn't ask for it, recall that this means it's source free. Okay, now going back, we could have, instead of finding n, because sometimes that is tricky, we could have used the second form. We already have f, g, and h. And the partial derivative was fairly easy to compute. So we could have used that form as well. We might have a difficulty trying to figure out our region. But it looks like we've got our x and y limits of integration already, so we could have tried that one as well. So this is it for this section. That's it.